In the previous video, I presented the integral test, a theorem that gives a relation between improper integrals and infinite sum. In this video, I will present some examples of how to use it. As a reminder, here is what the theorem says. I begin with a function that's continuous, positive, and decreasing between a real number a and infinity. Then I can say that the improper integral, obtained by integrating this function all the way to infinity, is convergent if and only if the series obtained from this function is convergent. And as a notation, in that case, we write a tilde between the two of them. This doesn't mean their values are equal, it means that they are both convergent, both a number, or that they are both infinity. I assume you have watched the previous video where I explained where this theorem came from. I will add a link in the description. So now let's see some examples of how to use this in practice. Most of the time, the examples all look the same. I want to know whether a certain series is convergent or divergent, and it happens to be easier to check whether the integral is convergent or divergent. The first example is probably the most important one, is the commonly called p-series. I want to know when the sum of 1 over powers of n is convergent. For every value of p, a real number positive, I get a different series, sum of 1 over n to the p. For some values of p, this will be convergent, for some, this will be divergent. Can I use integral test here? Yes, I can. If I fix p and I consider the function f defined as f of x equals 1 over x to the p, starting at 1, then this function is certainly continuous, is positive, and is decreasing, so I can use integral test. By integral test, this series behaves like the corresponding improper integral, so it's convergent if and only if the integral is convergent. And why is this useful? Because we already know what the answer is for the improper integral. We know that this improper integral is convergent exactly when p is greater than 1 and infinity otherwise. I will add a link in the description of this video to the video where I proved that for improper integrals, but it's an easy calculation. Just find the antiderivative and take the limit. Therefore, by integral test, we get exactly the same result for the series. And that's it. Now we got a new large family of series that we know to be convergent. For the second example, I will look at a very specific series, the sum from n equals 2 to infinity of 1 over n ln n. I want to know whether it is convergent. Notice I cannot start the index at 1 since ln 1 is 0 and I cannot divide by 0, but this series starting at 2 makes sense. I want to use the integral test, so I'm going to look at the function defined by the same equation, f of x equals 1 over x ln x. Starting at 2, this function is positive, decreasing, and continuous, so I can use the integral test. And by integral test, the series will behave like the improper integral, so one is convergent if and only if the other is. Why is this good? Because there's something else I can do for the improper integral, which is to actually find an antiderivative, and that's exactly what I'm going to do. The integral from 2 to infinity of this function is defined as the limit as b goes to infinity of the integral from 2 to b. So, what I need to do is find an antiderivative for 1 over x ln x, and then I will evaluate that antiderivative at b minus evaluate it at 2, and then take the limit as b goes to infinity. At this moment, perhaps you see what the antiderivative is right away, or perhaps you need to do guess and check. And otherwise, try the substitution u equals ln x, because its derivative is there. Either way, pause the video if necessary and find the antiderivative. And you will end up getting ln x. It's easy to check that it works. The derivative of ln x is 1 over ln x times 1 over x. So now let's evaluate. I get the limit as b goes to infinity of ln b minus ln 2. And as b goes to infinity, ln b also goes to infinity, albeit slowly. So the improper integral diverges to infinity, and by integral test, the series diverges to infinity as well. That's it.